Good morning, everyone. We're going to continue along in chapter 9 today. We'll hopefully just about finish through the content for midterm 4 today and spend most of our time Friday reviewing. We'll start lecture early on Monday, as usual, before our midterm week. So Monday morning, we'll start up 20 minutes early for some review content, probably push into lecture a little bit. At some point in lecture Monday, we do have to move on to some new material. And again, it's the remaining part of chapter 9. I think it might be a little bit reinforcing of some of the earlier topics that should hopefully help us for our upcoming exam. And then looking ahead to the final exam, we go through chapter 12, but only a couple small details out of chapter 12. We'll probably spend about one lecture on chapter 12. And then we have chapters 10 and 11 that are kind of more normal chapters. We spend about 3 lectures on each. Okay, so before we get into this slide, I wanted to come back to the issue of polarity. And I just kind of resketched a bunch of Lewis structures for a lot of things that we'd already had in our notes previously, like CF4, I think we had CCl4, but CF4 has 4 valence electrons for carbon. If we were double checking our Lewis structure, we might be just checking our valence count, 4 for carbon, 4 times 7 for the chlorines, that's 32 total electrons. Multiple of 8 electrons will tell us that we're just going to have the 4 fluorines with 8 electrons each around them. So no electrons left over for carbon. Just making sure that we see we have 4 total domains. All of them are bonding. So our geometry is tetrahedral, our electron domain geometry is tetrahedral. But then the polarity of the molecule, because these fluorines are all equally electronegative, they're all pulling equally as hard on the carbon atom, creating the exact same negative charge around the molecule, such that the molecule is nonpolar. So even though this molecule truly has really polar bonds, it exists as a nonpolar molecule. Now, how can you picture the difference between polar or nonpolar? Well, 2 key differences could be, would the molecule be attracted towards a charge, or would it just fight over the charge? If we put a positive charge over here, all those fluorines are just going to fight over it. Either one's going to be able to win and pull the molecule towards the charge. Another thought could be, if you had 2 adjacent molecules of CF4, would they experience some kind of attraction or repulsion? They'd actually experience probably more repulsion than attraction, because you have all the negative charges repelling each other on adjacent molecules. So we need somehow one side of the molecule to adopt a different charge than the other side, but we have to take into account all 3 dimensions of side. So if we have any of the base geometries, if you go linear, trigonal planar, tetrahedral, trigonal, bipyramidal, or octahedral, and you have the exact same atom in all spots of the geometry, then the molecule is going to have to be nonpolar and not have one of those dipole moments. The implication later, we'll see this a little bit more in chapter 11, is that molecules that are nonpolar have generally weaker attractive forces with themselves, so they're going to be more likely to be gases at room temperature or have a weaker attractive force. And so there's a big property difference between polar versus nonpolar molecules. Now, if we do something to disturb the nature of the charge, like if we take a molecule kind of like CCl4, but we replace 2 of the chlorines with hydrogens, this molecule here, CH2Cl2, this is called dichloromethane. So it looks like methane, or a lot like the CCl4 example, just where we replace 2 of the chlorines, what could have been chlorines, with hydrogen atoms. And then that's enough to disturb or change the charge nature so that our chlorines are the most electronegative atom. They're going to pull electrons towards themselves. The CH bond in and of itself isn't particularly electronegative. The electronegativity difference between C and H are pretty similar. So there's not a huge difference. Most hydrocarbons aren't going to have any kind of dipole moment or any large dipole moment associated with them. So the idea here is that this negative charge is not balanced by the charge on the hydrogens. Therefore, this molecule would be polar. So if we do anything to change the geometry of the molecule such that we don't have a perfect balance of atoms on one side versus the other, then we could have an example of a polar molecule. Like if we go to CF4, if I take this example, let me change colors here. If I take this example and say, well, let's change one of these fluorines to like a chlorine atom, and instead of the fluorine, we have a chlorine in its place, that would be all it would take to make that molecule polar, because then we wouldn't have the exact same charge on every end of that molecule. So think about how the charges are balancing out. You could think of when it's CF4, all those dipoles, if you imagine the dipoles pointing in this way here, mathematically would cancel out. That's a geometrical way you can imagine that when we have perfect dipoles, they cancel out. In the case of CH2Cl2, they wouldn't perfectly cancel out. If we replace one of the fluorines with a chlorine on CF4, then they wouldn't perfectly cancel out, and we'd end up with a polar molecule. So CF3Cl we call that molecule polar. So if I take SF6, SF6 has a octahedral geometry. We have 8 electrons around each of the fluorines. Just to double check our count, 6 for fluorine, 6 times 7 for the fluorines. That's 48 total electrons. And again, a multiple of 8 times 6 fluorines. That's 8 electrons around each of the fluorines. We have here also a perfectly nonpolar compound despite having truly polar bonds. So these bonds are pulling electrons away from sulfur. In fact, we mentioned earlier, and I'll re-mention it here, that the electronegativity of fluorine is really what allows sulfur to expand its octet. The Lewis structure of sulfur shows an expanded octet. It appears that sulfur has too many electrons around it, but the fluorines are like, hey, we'll help you out. If you don't really need those electrons, we'll take them away for you, and we'll pull them closer towards ourselves to help make some room around sulfur so that it really truly doesn't have as many electrons as you might think, based on the sort of octet rule appearing to be expanded based on the Lewis structure that we wrote. So the electronegativities of fluorines pulling electrons away from the sulfur atom, making room for all those electrons around the sulfur, but then not allowing the charge to develop that's different. So all the charges on the end of the molecule are exactly the same as each other. So again, we'd have a perfectly nonpolar molecule. So we could switch one of the fluorines, like a chlorine or something. Maybe it's not a real molecule, who knows? Some of these examples are hard to come by, like SF6 does truly exist. You can put it in a gas cylinder, but if you start playing around with the bonds, you want each of the bonds on an axis to be the same, and then those dipoles are going to cancel for something like SF6. What about SF4? Do you guys think SF4 is polar or nonpolar? So let's think about the fluorines that are opposite. These dipoles just about cancel each other out. They don't perfectly cancel each other out because that bond angle is not perfectly 180. If you remember, this was like 186 or something like that. The internal bond angle is about 174 degrees. So because of the electron pair, it's actually pushing these fluorines closer together. It's pushing these fluorines closer together as well. So this bond angle is not perfectly 120. It's a little less than 120 degrees. So that electron pair is having the impact of perturbing the structure. It's going to then take what would have canceled perfectly at 180, not exactly canceling, but then I have these two dipoles pointing this way on the molecule too for the fluorines. So we have a big negative charge on this side of the molecule here that's not balanced on this side of the molecule. So the left side of the molecule doesn't have the same charge as the right side. Therefore, we have a molecule with different charges on its ends. Therefore, we have a polar molecule. So we're going to have a polar molecule. Generally, like if you can see the structure perturbing, like with an electron pair. So if we take one of our base geometries, add electron pairs, generally we're going to end up with something that's polar. If you look at like SF2, water kind of has the same bent geometry within tetrahedral. So if you have a tetrahedral geometry with the two lone pairs and you're a bent bond, water's of the same geometry, it was polar. SF2 was polar as well. So the two key details that you need for a molecule to be polar is you need to have polar bonds. If you notice, most of these examples have a really electronegative atom like oxygen or fluorine. In fact, all these examples have fluorine or chlorine. NOFCl are the four most electronegative atoms. You pair them up with anything but themselves, that's going to make for a polar bond. And so the SF bond's certainly polar, but then we need the bonds to be situated in such a way that the molecule can adopt a different charge on one end versus the other. We have these electronegativities pulling towards the fluorine, negative charge over here, a partial positive developing on the sulfur. Same thing in SF4, partial positive on sulfur. So we have a positive end of the molecule, a negative end of the molecule. Therefore, we have a polar molecule. Now, when you think about the ends of the molecule being different in charge, think about how SF2, this side, I need the exact opposite charge, like on CF4, opposite it to be the exact same charge. I don't have that on CF4, or on, on SF2, so SF2 is polar. Sometimes we get a little confused by the presence of electron pairs, and we say, well, wait a minute, aren't the electrons negative in charge? Yes, electrons are negative in charge, but charge usually resides, we think about the nuclear charge, that's like left over on the nucleus of the atom. So we have a net positive charge on sulfur. That's what can pull in another molecule of SF2. So if you can imagine a second SF2, then we're going to have this built-in attractive force between this positive charge here and then this negative charge here. So we're going to have that attractive force that's built into the molecule. The electron pairs, if you remember, are really small, and they're really not in the way. The nuclei are what carry a majority of the mass. So we're kind of looking at how do the masses interact with each other, and what charges do they have? Yes, electrons are negative, but they don't exactly have the same negative charge as the fluorines, so you need the exact same charge on the electrons, but you really need a nuclear center to carry that charge and to balance it out perfectly, like in CF4, where it's the exact same atom within that geometry. What about ClF3? This is probably, hopefully, pretty easy that you can predict this easily, that this one is polar because we have the electron pairs. We're pressing these bond angles closer together. They're not even perfectly 180. This bond angle here is less than 90 degrees, so we have a polar molecule. Xenon F2, if we were to go through trigonal bipyramidal geometry, perfect trigonal bipyramidal, meaning exact same atom in all 5 spots, trigonal bipyramidal like PF5, that would be nonpolar. Then we see SF4 is polar, we see ClF3 is polar, Xenon F2. What about this structure here? Do you remember how we mentioned that this bond angle is actually perfectly 180 degrees? Those dipoles cancel perfectly, just like CO2. So Xenon F2 would go back to being nonpolar. So there's a lot of examples on quizzes. Just go through a few examples and make sure you can sketch the structure, see the shape of the molecule, think about what its geometrical name is, try to picture the shape of the molecule and just think, is one side of the molecule a different charge than the other? Okay, so let's come back to this topic here of having multiple central atoms and going through geometries of molecules of things like acetic acid, for example. Within writing Lewis structures, you'll see Lewis structures predominantly written flat, where it's really easy to write the structure like we wrote here, where we're not trying to depict the three-dimensional shape. If I then say, well, what's this bond angle here? We do this a lot on tests, and a lot of times we get 90 degrees, but that's not necessarily going to be the right bond angle. Same thing with this bond angle here. Is this bond angle 180 degrees? No, because we have to interpret the shape. So even though we may write it 180 degrees, that's just for the sake of simplicity. The actual 3D shape has to be interpreted based on the number of domains. So if I want to know this bond angle here, I have to look at 1, 2, 3, 4 domains. This carbon here should be tetrahedral. So that carbon being tetrahedral, because it has 4 bonding domains, no non-bonding domains, so 4 total, should be tetrahedral domain. Therefore, these bond angles have to be closer to 109.5 degrees. So if we're picturing the structure, it would have to look something like this. Have to use like wedges, arrows to depict the structure. And so let me actually rotate it and write it slightly differently. Let's write it with the bonds this way and the wedge and arrow coming this way. Doesn't make much of a difference, but it'll help us write the next kind of group here, where we're thinking this carbon here is bonded to another carbon that's bonded to an oxygen, that's bonded to an oxygen. Then we have lone pairs. Now we might think, where are the lone pairs? Maybe coming straight out, maybe going back into the page with our lone pairs, and then straight down. So that's a lot harder to sketch. Like if I wanted to sketch that picture, I gotta use like a more sophisticated program to build a structure to show its shape. But we can interpret the shape. I can interpret the shape that, from our flat structure, that these angles should be 109.5. That's why I sketched them the way I did. That these bond angles here should be closer to 120. We can even predict that the double bond angle should be a little bit greater because the double bond repels the single bonds a little bit more than the single bonds repel each other. That's a fine detail. You'll see a couple questions on some practice exams that get at that kind of topic of just double bonds repelling the single bonds to a slightly greater extent, just like our lone pairs repel the bonding pairs to a little bit of a greater extent. And what we would have expected to be about 109.5 degrees for that COH bond angle, this bond angle about our oxygen atom, we would have expected that to be closer to tetrahedral's bond angle, but because of our electron pairs, we're going to predict it's a little bit less than 109.5. So you can predict bond angles to be close to, should you expect tetrahedral, trigonal planar, linear bond angles, and then you can usually predict even if it should be a little bit less than those bond angles. So again, like the structure here, this really isn't a 180 degree bond angle. We have to interpret that that's trigonal planar. So this carbon here is trigonal planar, so it should be closer to 120. Then we go back to tetrahedral domain, bent bond for that last oxygen. So we're kind of assigning an electron domain geometry for each of the central atoms within the molecule, and then from there just predicting our bond angles. Now you can predict the bond angles without sketching the molecule like this, so you don't always have to re-sketch the molecule. It might help you picture it. It might help you picture, well, it looks like 90-degree bond angles, looks like the COH bond angle, looks like this bond angle is 180 degrees, but you just have to interpret the shape to get the bond angle. So another example here, and again, we have another tetrahedral, so we have a tetrahedral geometry with 4 domains. So this should be close to 109.5 degrees. And then these 2 carbons here are just linear. And so those should both be 180 degrees because they each have 2 domains. So the triple bond's 1 domain and the single bond's another domain. So we have 2 total domains for the next carbon atoms. So they're both going to be linear. So sometimes the bond angles look 180, and they are 180. So sometimes the bond angles look like what they truly are, and sometimes they don't. And again, if we're sketching the structure, you don't necessarily have to do this part, but if we want to sketch this probably the same way as before. So the molecule looks planar in our lowest structure, but it's really not planar. It's really not flat. Okay, let's get into the nature of how these bonds form. You know, try to get a better description of the bonding in these molecules. We do this through a theory called covalent bonding and orbital overlap theory. We'll also discuss something called hybrid orbital theory that goes along with this. And the basic idea of orbital overlap theory is bonds form when orbitals with electrons can overlap with each other and exchange the space and share space together. So a hydrogen bond can be described by taking like the 1s electron and pairing it up with another 1s electron and allowing those 2 orbitals just to mix together and pair up together. And so you would imagine this will tie together a little bit with MO theory. Molecular orbital theory is in our sections that won't be covered for midterm 2 that we'll talk about more on Monday. But in MO theory, we'll see that there's a molecular orbital that has a spin up and a spin down electron. So we kind of come back to Hund's rule, 2 electrons going into an orbital, spin up, spin down. We'll see a little bit more of that later. But within orbital overlap theory, we're just saying, okay, we got a 1s orbital here, 1s orbital here. What if they just exchange and kind of occupy the same basic space? And so this is why hydrogen ends up forming a bond. It turns out bonds will have an ideal bond length. Hydrogen's is about 0.74 angstrom. If we go too short, the energy goes back up, or potential energy increases. And then if you lengthen the bond, the energy increases as well. But eventually plateaus where we get to 2 hydrogens that have just been separated from each other at 0 relative potential energy. So 2 hydrogens separated, brought together, they form a stable bond together. And so we can picture the bond in like hydrogen chloride and the molecule of HCl with a single bond, just as the 1s of hydrogen overlapping with that largest orbital of chlorine, the 3p. So we're just taking a look at chlorine and kind of seeing, well, chlorine's a 3s2, a 3p5 configuration. So we have this one unpaired electron. So we're kind of pairing electrons up that are unpaired through the overlapping of orbitals. And so we can describe the orbital here like this, or the single bond as a 1s 3p overlap. So the 1s of hydrogen and then the 3p of chlorine. 2 chlorines would just be 3p 3p overlap. So we just overlap those extra electrons. So we just take the 3p electrons of each of the atoms that are unpaired and pair them up together and make a single bond. We can picture double bonds versus triple bonds compared to single bonds. So we can try to make kind of a basic diagram of what these might look like. Let me just start with a basic picture of what a carbon-carbon single bond might look like. So let's just hypothetically kind of think it'll look a lot like the carbon bond, where it'll have some ideal bond distance, and then it'll separate into the 2 carbon atoms. And so this is our single bond. And so then let's think about how the carbon-carbon double bond will look different, because the carbon-carbon double bond will be shorter than the single, but then also stronger. And so bond strength is implied by how far down we go, and then the bond length is depicted by the distance here. So this is our bond length, our equilibrium bond length for carbon-carbon single. The ideal, the lowest bond length is longer than the carbon-carbon double. Might have made more sense to make this a different color. Let me overline this with blue to show the carbon-carbon double. So the carbon-carbon double looks shorter, and then it goes deeper, meaning it's a stronger bond. So the energy it takes us to go from here all the way to separation, that's our bond strength. So the stronger the bond, the deeper the potential well goes, and then the shorter the bond, the closer towards zero we go. So if we go to the carbon-carbon triple bond, we should go even deeper and then shorter. So stronger bond and then shorter bond. So you can kind of see how that plays out in terms of a diagram, an energy diagram for a bond will look like the hydrogen bond, but just kind of going to a shorter bond as you go to double versus triple bonds and then going stronger at the same time. So just showing that you're shifting the RE to the left and then the energy downward. Now, what we still need to describe is, well, what is the actual bonding nature in double bonds versus triple bonds? The single bonds you can probably imagine are some sort of like p orbital overlap. But for carbon atoms, we're going to need a little bit of a larger bonding model to take into account how they have more orbitals in order to understand their some like theories, or to get this bonding overlap, we'll need to develop some more theories for things like carbon atoms. So that's where like the theory called hybrid orbital theory comes into play. Some atoms, we can't easily just show an orbital overlap model like we could for HCl, for Cl2, or for H2. When we have a molecule like BeF2, and we're trying to understand the overlap on how we get two bonds to form with fluorine through its best Lewis structure. We've written this Lewis structure before where we've noted BeF2 is okay, not satisfying the octet rule for beryllium. If we tried to make double bonds, beryllium would have two negative of a charge. Fluorine would go positive. Fluorine wants to do the opposite. It's trying to pull the electrons away and go partial negative in its charge, and the beryllium truly should have some sort of partial positive. But in terms of the bonding nature, how can we take beryllium, which appears to have a spin-filled 2s orbital, so it has two s electrons and an s orbital that are like filled with electrons, how are we going to get overlap with p orbitals of fluorine? So we would probably picture fluorine's largest orbital. Let me switch back to a normal color. So fluorine would be a 2s2, 2p5, just like chlorine was. So fluorine should have this one unpaired electron. So we're picturing fluorine with some sort of 2p orbital. How am I getting overlap? How would I get overlap with beryllium? Well, the way we're going to get it is by totally making up orbitals. We're going to just take the 2s and the 2p orbitals that beryllium has, quote unquote, at its disposal. So it has the access to the orbitals. It has in its ground state electron configuration a 2s2 configuration. Well, what if we do two things? Let's move one electron over to the 2p subshell so we can have a 2s and a 2p. And then let's do something called mixing and just imagine that this s electron, this p electron, the 2s and the 2p for beryllium kind of decide to change shape, and they form two different orbitals. They form orbital number 1 and orbital number 2. And they just look like kind of like p orbital hybrids that point in each direction of 180 degrees. And so you take these orbitals, mix them together, allow them to hybridize, and you get orbital number 1 and then orbital number 2. So one of them points in one direction, the other direction with 180 degree bond angle. Now, this is not true math. This is just a model kind of saying, well, what if we end up with these two things? We call them hybrid orbitals. And so we call these the sp hybrid orbitals. So this would be sp orbital number 1. This would be sp orbital number 2. So we get two sp orbitals because we took two atomic orbitals to construct them or to mix together to give us these orbitals. We then leave behind these two p orbitals. So these are unused. We'll see later for other molecules how they can be used, and what we'll see is pi bonding, but we'll find ways to use these orbitals in other molecules later. But for beryllium F2, these are just empty orbitals. So you can imagine on beryllium, and it might be useful to think you have an orbital that looks something like this. We have an orbital sticking straight out. We have those two p orbitals that don't do anything, that don't have electrons in them, that are just empty. So keep those in your mind for later, so other molecules will try to find something to do and use with those orbitals. But so then with beryllium F2, I then have one electron in like one of the orbitals, one in the other. So I now have an sp, each with an unpaired electron that can pair up with the unpaired electron of fluorine. And so I've just created orbitals where I can get this orbital overlap, and I created orbitals where I have like one electron in each of the orbitals. Okay, in a way, this is kind of fiction, but it's a bonding model that helps us describe the bonding in molecules. It kind of ties into the notion that, if you've ever heard this expression, that all models are wrong, some are useful. And so this model technically is kind of wrong in a way. Like the orbitals really don't exactly mix together the way we're depicting, but it does give us a model that helps us explain how we get two equivalent bonds, which is actually true for beryllium F2. We get two equivalent bonds that look the same as each other through this type of bonding, or this type of bonding helps us understand how that can be. Now, before we figure out what to do with those unused p orbitals, let's just run through the other two hybrid models that we'll go through, those being sp2 and sp3. And let's look at a quick example of a molecule that goes sp2. Now BF3 instead of BEF2 is going to need a little bit of a different bonding model because we know we have 120-degree bond angles perfectly around this molecule. We know this is the best Lewis structure. We know the fluorines are trying to pull electrons away from the boron. We know all of that from Vesper and just our relative differences of electronegativity. But now for boron, we need 3 orbitals instead of 2. So the sp2 model doesn't work because we just have 2 orbitals this way and I have 3 bonding partners we need to make bonds with. So what if we do use an extra orbital on boron? So let's take boron's original configuration, just boron from the periodic table, would be a 2s2, 2p1. That's a weird sound. So it would be a 2s2, 2p1. Well, what if we just change that to look like a 2s1 and then a 2p2? And so we now have 3 unpaired electrons, but not really in the right orbitals, allow us to click together to make our 3 bonds with the fluorines. So what if we then mix those together? So we take the S and then 2 of the P's and mix them together. And then the p orbitals you're going to want to choose would be in the plane of where the fluorines are. So if you're choosing the p orbitals, you want them to be in the plane of where the fluorines are. So I'm going to pick the p orbital in this plane and the p orbital in that plane, if that makes sense. I'm going to leave behind the p orbital like bisecting the molecule. So I'll have one leftover p orbital that should be sticking straight out of the boron atom. So then when I mix and hybridize my orbitals, it's hard to sketch this missing orbital that's unhybridized, but I have this leftover unhybridized orbital sticking like straight out of the page. Now, again, BF3 is not going to use that orbital, so we'll erase it for now and come back to it later. But for BF3, we use these now sp2. So we call this sp2, p2, because we're using 2 of the p orbitals. And then we get 3 orbitals. So we get 1, 2, 3 sp2 orbitals. And then they each could be thought of as having, that one unpaired electron that's ready to pair up with something like the unpaired electron on a fluorine. So we can take each of these with a fluorine and then overlap. It's a little too far away. So let's take the fluorine with a 2p and then pair it up to make our bond. And so we do that on either side to make our BF3 molecule. So the key is we're just creating orbitals where we believe there should be orbitals to make orbital overlap. So hybrid orbital theory just kind of bridges from covalent bonding theory or the orbital overlap theory that says if orbitals form because of the overlap of orbitals and I don't naturally have orbitals where I need them to be, let's just make them up and put them there so that we can get the orbital overlap that we think should be there to form these bonds. And so we end up forming 3 equivalent bonds in BF3. So in BF3, the bonds would be described as being the sp2 2p overlap. So the sp2 of boron and then the 2p of fluorine. So fluorine, we don't have to hybridize. We can see it has that 2p orbital with an extra, just 1 electron that it's going to pair up with. Then the last base model for hybrid orbital theory is sp3. Tetrahedral molecules will need sp3 bonding. And if you think of tetrahedral molecules, they need orbitals that are 109.5 degrees relative to each other. So I need orbitals, ideally, 109.5 degrees around that carbon in order to be able to pair up with things in this tetrahedral geometry. And so if I look at my p orbitals for carbon, where again, we're thinking carbon kind of looks like a 2s2, 2p2. Well, let's first kind of make it a 2s1, 2p3. And then let's let these orbitals mix together and change form and change shape. Now, this isn't math. This is just literally like voodoo science. This is just literally, well, let's take what was orbitals pointing 90 degrees relative to each other in the p orbitals, and then the s orbital in between, and take those 4 orbitals and create 4 new orbitals, call them the sp3 orbitals. There's 4 of them. So I get 4 sp3 orbitals because I took 4 atomic orbitals, changed them into the 4 hybrid orbitals. Just like sp took 2 atomic orbitals, turned it into the 2 sps, sp2 took 3 atomic orbitals, turned it into 3 hybrid orbitals. So here we take 4 atomic orbitals, turn them into the 4 hybrid orbitals, and just magically they're in the shape of a tetrahedron at 109.5 degrees. And so then this shows us that we can kind of think of something like water as having the structure of this tetrahedral geometry using these that's a 2, not an S, using the sp3 orbitals. And then just putting electron pairs, sometimes we call these rabbit ears, but we put the electron pairs under the oxygen, just into the spot on the tetrahedron. And I've been kind of sketching these orbitals even back, as far as introducing water's geometry, like when we first started chapter 9. And CCl4 does the same kind of thing, so we can describe these bonds with hybrid orbital theory as being the sp3 orbitals of carbon overlapping, now because it's chlorine, not fluorine, it's the 3p orbitals of chlorine overlapping with the sp3. So we can see that we get this hybrid orbital, atomic orbital overlap to make those 4 bonds in something like CCl4. Now, hybrid orbital theory, if you ask me, is pretty simple. When I'm looking at a central atom, if I can tell it's tetrahedral, I know the atom has to be sp3 hybridized. If I'm looking at a central atom that I know is trigonal planar, then I know it has to be sp2 hybridized. And if I'm looking at something that I know is linear because it has 2 total domains, it's just sp hybridized. So in a lot of ways, we don't get any more of a description than what we already had from Vesper with this theory. But what we're going to see in a moment is that we can describe pi bonds really, really well. And so the leftover p orbitals in sp and sp2, those leftover orbitals we haven't found anything to do yet with, we're going to make double bonds and triple bonds out of those. And that bonding picture is going to be really accurate in terms of what multiple bonds really look like in finer detail. Okay, so a quick summary would be, linear is sp, trigonal planar is sp2, tetrahedral, sp3, and just anything to be linear, 180, fits into the sp model. A lot of examples that are trigonal planar. So you can think of a bunch of examples that fit into these models here. But the next question will be, or the next issue will be, well, let's take a look at the pi bonding within the leftover p orbitals that we know that we have with the sp and the sp2. We're not going to get pi bonding with sp3 because we've used all the p orbitals. This then will go back to those goofy Lewis structures. Remember for like PO4 3-, where we had 4 single bonds, and we were like, should we make a double bond? We really can't make double bonds on things that are tetrahedral, at least not with any model I know of. So we're not really going to be able to make pi bonds with SP. So can I make pi bonds? I should be able to make up to 2 with SP. I should be able to make up to 1 with sp2 because I have 1 leftover p orbital. I should be able to make 1 pi bond, and I'll make 0 pi bonds with sp3. So let's take a look at the pi bonding. So if I look at a simple molecule CH2, CH2, could be C2H4 written this way here, that this is the molecule called ethylene. And so we have 2 hydrogens here. And so then our carbons we know are going to be, what hybridization would you say those 2 carbons are? SP, sp2, or sp3? Just sp2. And we're just evaluating, each of the carbons have 3 domains. No lone pairs on carbon. So we have sp2 centers because they're trigonal planar. Now, picturing those as sp2 lets us say, okay, the carbon is going to take, and this becomes a little bit of a tricky problem of trying to picture, well, where are the hydrogens? Because whatever plane those hydrogens are in are the same plane we want to take the p orbitals from to hybridize to make our purple hybrid orbitals. And so the picture here kind of has the hydrogens coming in and out of the page. They have them coming in and out of the page so that we can then see that the leftover p orbital that we did not hybridize is the pink one. It's this one here, that this orbital here is now right in the plane of our paper. So that plane of the paper is going to bisect the bond of the hydrogens. Okay, that helps us then see that if we then line up the other hydrogens in the exact same fashion, so these hydrogens coming out at us, coming back, coming out here, or where our hydrogens are, we then have the other leftover p orbital. And doesn't it look like those p orbitals are ready to line up and overlap with each other? All they need is an electron in them. So all they need to overlap is an electron to go into the bond in order to make use of that set of orbitals. And that type of bond looks a lot different. Like if we're talking a bond this way versus this way, they have a fundamental difference in their shape. A bond that's this one here, this is symmetrical about the bond axis. Whenever you see a bond and the electrons are in the center of the bond, symmetrical about the axis of the bond, we call that type of bond a sigma bond. And then anytime you have a bond that looks like this one here, where it's now in the plane of the bond instead of the axis of the bond, that's like a planar bond. So notice that looks more like a plane. So we call it a planar bond or a pi bond. So we get that pi bond to form between the p orbitals. Now, when we look at carbon, if you think of carbon like we did earlier, where we were kind of saying, okay, imagine it does this and you hybridize, but now just these ones to sp2, each with an unpaired electron. And then here we now have that p orbital with an extra leftover electron. So if you go back to like the BF3 example, like BF3 needed sp2, only had 3 electrons to begin with, but carbon has 4 electrons. So carbon has that extra electron because it's a larger atom, and therefore it's going to have 1 electron that's in that leftover p orbital, the other carbon the exact same, so therefore we have electrons that can make use of that pi bond and make a pi bond. So anytime we see a double bond like this here, we can imagine that I have a sigma bond and I have a pi bond as part of that double bond. The sigma bond is the sp2-sp2 overlap. So if you notice the purple overlap, the sigma bond, this is our hybrid orbital overlap. So that's the overlapping of the hybrid orbitals. Hybrid orbitals are on the axis of the bond, so they have to be sigma in nature. So it's just showing you your sigma bonds, symmetrical about the bond axis, pi bonds, symmetrical about the plane of the bond axis. And so then if you look at the single bonds between hydrogen and carbon, we can describe these bonds too. So the carbon bonds would just be 1s of hydrogen overlapping with the sp2 of carbon. So we have the sp2 orbitals of carbon overlapping with the 1s. And so those are shown here. Now, we'll ask questions sometimes. They're like, well, how many total sigma and how many total pi bonds does this molecule have? Well, it has a total of 1, 2, 3, 4 plus 5 sigmas, but then just 1 pi bond. Now, the confusing part sometimes is you think the double bond, the mistake we make a lot of times is thinking a double bond is 2 pi bonds. The double bond is the sigma hybrid orbital overlap, and then the extra bond that makes it double is the 1 pi bond. So remember, your double bond is just 1 sigma, 1 pi. Okay, so pi orbital overlap, this is a really good model. This is a good prediction that we get from hybrid orbital theory for what double bonds look like, that they're putting their electrons more into the outer peripheries of the molecule than our sigma bonds are. Let's look at a triple bond. And so we should be able to come up with a simple picture for what acetylene looks like. Acetylene is H to carbon triple bond to carbon single bond to hydrogen. So this is C2H2, where we now have a triple bond between carbon. And so then for carbon here, we're probably picturing sp hybridization because we have linear geometry. And so then I'm picturing having sp orbital number 1, sp orbital number 2, about the 1 carbon, so picturing just something like that. And then the same overlap for the other carbon. And so my 1s sp overlap is my description of the bonds between hydrogen and carbon. So 1s of hydrogen, sp of carbon. but then carbon has 2 leftover p orbitals. I don't know why I'm sketching it, but like sometimes by sketching it, you can try to see, okay, that's this orbital here. And again, carbon had started this whole picture off with, if we go back to the picture of hybridization, starting from this picture here, where we're taking the 4 electrons of hydrogen in the 2s and the 2p subshells and saying, well, let's just hybridize these and come up with sp, putting an electron into each, and then having 2 empty p orbitals with an electron each. So we have the 2 p's left over that are unhybridized with electrons in them as well. So now I have electrons in these bonds here that can overlap, and then I have electrons in the other p orbital. The other p orbital being in the other plane. The 3 dimensions is what makes this hard to see, is that if we're picturing carbon making sigma bonds in this, call that the z. Let's imagine this is the z-axis. It doesn't matter which one you call it, but let's just call that the z. Then let's call this one the x. Well, then this plane here would be the y. So we get the px orbitals overlapping in one pi bond. Then I need the py orbitals to overlap in the other. And so you can kind of see that this looks like here, the py orbitals overlapping to make that second pi bond. So our triple bond can be described by the sigma bond of the overlapping of the hybrid orbitals, but then the 2 pi bonds. The 2 pi bonds from the 2 sets of p orbitals that are left over from the hybridization process. So we have electrons in those p orbitals that overlap and make those pi bonds. And so in terms of total count here, we'd have sigma bond here, sigma bond for the CH bonds. So our sigma bonds are from the hybrid orbital overlaps. So the 1s overlapping of the hybrid orbital, that's symmetrical. Like this bond here is certainly symmetrical about the bond axis. This bond here is symmetrical about the bond axis. And that bond there is symmetrical about its bond axis. So I end up with a total for the molecule of 3 sigma bonds. And then I have the pi bond number 1 and the pi bond number 2, plus the 2 pi bonds. So like a single bond generally is a sigma, a double bond is a sigma and a pi, and then a triple bond is a sigma and 2 pi. And so then breaking this down, like you don't necessarily need to sketch out the geometries of the molecules or all these orbitals to kind of picture that we don't need any hybrid orbital picture to get the sigma bond between 2 hydrogens. When I look at acetylene, okay, the double bond is the sigma and the pi. The triple, even if we look at N2, without even knowing much of anything about N2, you can just look at that being triple and say, okay, I'm getting that there should be some sort of overlap here, and then the p orbitals overlap here, and then here. So you can sketch them out, that might help, but you can see that you're gonna get sigma bonding and then p orbital bonding. So our triple bond in nitrogen, 1 sigma plus 2 pi. And then here we can look at this being sp2, and then we're going to get overlap. Now oxygen, you can do 1 of 2 things with oxygen. You can just leave it alone and use its p orbitals, or you can see that, well, it probably too could be sp2 because it has 2 lone pairs and a bonding domain, so 3 total domains as well, like carbon. So what if we picture that as being sp2 as well? And so we get our sigma overlap for one of the bonds, and then our p orbital overlap for the other one. So it should be a sigma plus a pi for the double bond, and these bonds here should be sigma bonds. So in total for the molecule of CH2O for formaldehyde, that would be a total of 3 sigma plus the 1 pi. And then the sigmas for the hydrogens would be 1s sp2 overlap. So those are the CH bonds. And the CO double could be described as sp2 sp2 overlap for the sigma, and then the leftover p orbital overlap for the pi. So the pp overlap or the 2p overlap, just the leftover unhybridized p orbitals of carbon and oxygen overlapping to make that pi bond. This molecule here, again, it just comes down to tetrahedral, so sp3 for the carbon here. It comes down to linear, so sp, linear, so sp for nitrogen as well. So we get sigma number 1, 2, 3, 4, 5. So I get 5 sigmas and then 2 pi. In total for CH3CN. So you can break down without sketching the p orbitals and just look, anytime you see a triple, just know it's a sigma and 2 pi. Pretty straightforward, hopefully. Now, we come back to this picture, we saw this in chapter 8. Let's take a second look at this for nitrate. So nitrate, if we're looking at any one of our 3 possible resonance structures where we have the double here, here, or here, and we're trying to think, okay, what would the Lewis structures look like when we take a look at any one of those structures? If I have what we would call a localized double bond is a bond exactly where you think it is. So if we want to localize the bond here, then we would sketch a structure that shows a double bond in that particular location and single in the others. And so then that would look something like this here. This might depict this structure here just geometrically in terms of where the oxygen double bond is shown. So localizing the double bond to this particular location here arrives at this structure here. And then notice that if you then say in the other Lewis structures that oxygen is sp2 and the other 2 Lewis structures, and when it's sp2, it has a p orbital that's left over in the hybridization process that's pointed kind of in that same general direction as the pi bond of nitrate. So we end up with these orbitals that are all overlapping in the same direction. Well, what if they all simultaneously overlap together and make one extra bonding orbital that the double bond goes into? This is the resonance picture. This is the resonance model where one orbital shares that extra 2 electrons in this double bond here across the other 2 bonds simultaneously. So this is how you can get the picture of nitrate really not looking like any of these structures here, but looking more like that composite structure that we've talked about a bunch, where it kind of looks like that 4/3 bond on average. So instead of it looking like a double and 2 singles at any given moment, it always looks like kind of a combination of those bonds because we have one orbital sharing that double bond, that extra pair of electrons across all those 3 bonds simultaneously. Now this kind of shows you then, if you go back to the picture for like PO4 3 minus, for like something like phosphate, which if you remember, had these 4 bonds to oxygen. 4 bonds to oxygen goes tetrahedral, no lone pair on phosphorus. And so when we're in this model here, if we're thinking hybrid orbital theory too, phosphorus, we're thinking it's probably sp3. For being tetrahedral, like where do I get the double bond, like p orbitals from, to overlap with phosphorus to make a double bond? So if we're thinking, should I go to a Lewis structure that makes this double bond here, I'm just like not quite seeing how we're gonna make that double bond. And then even if we did, how it could possibly resonate and then lead us to a model where all those bonds are actually equivalent and phosphate's bonds are all equivalent experimentally. So this is kind of just shows us that that's not really a good Lewis structure for something like phosphate. It's probably, you know, our textbook is too wishy-washy on the topic, so we kind of have been wishy-washy too on, well, maybe you can consider these as valid Lewis structures. I suppose you can. A lot of people sketch those Lewis structures. Oddly, you see them a bunch in OChem because organic chemists, the last thing they care about are accurate Lewis structures of inorganic molecules like phosphate ion. So you'll see Lewis structures sketched like the one I'm crossing out here in OChem, unfortunately, a bunch. But I think it's just like categorically incorrect to think of that as being a good Lewis structure, because I'm not sure where we're getting a bonding theory to get the double bonds, and even if we did within a tetrahedral molecule, how it could possibly resonate like it does in nitrate. So nitrate being flat really helps it form those resonance structures. Another molecule that Another molecule that does this a lot, that you see a lot in OChem, is benzene. And we can sketch benzene. Now, at the vertice points, this is something that you'll learn within like the first day of OChem, is that anytime you see a structure that looks like this, it's that you're imagining each of the points as a carbon atom, and then each carbon has enough hydrogens to give it a saturation of 4 total bonds. And so like the first one here would need 3 hydrogens. The middle would have 2 hydrogens. And I'm not really trying to teach you this so much, but you'll see this a lot in OChem, so at least you get a little preview here of what it means to kind of have these structures where you could have like a structure like like this, and just each vertice points a carbon with enough hydrogens to give 4 total bonds to each carbons. And so in the case of benzene, you would just have 1 hydrogen because each carbon only needs 1 hydrogen to come up with a total of 4 bonds. We have 1, 2, 3, 4 bonds now to each carbon. So this would be C6H6 in terms of its formula. And then you could sketch the resonance structure. So the resonance structure would just move these double bonds over to here, and then you'd have this structure here that looks exactly the same, other than we move those double bonds over to a different position, and then those would be what we call resonance structures. And then benzene never really looks at all like either structure A or B. It always looks like the composite. Probably a better way to do this is with a dashed ring like this. But you usually see the solid ring, just more colloquially used for benzene. So benzene, you usually see the solid ring, and you interpret that as the dash ring to interpret that it's really not single or double. So it's the averaging out of a double versus single. So each of those bonds, if I were to say for benzene, what's the average bond for the carbon-carbon bonds? Not quite double, not quite single, it's the average of that. So do you see how each bond would be a 3/2 bond? So it'd be like a double plus a single averaged out to like a 1.5 bond. But anyways, the delocalized picture of benzene looks just like this here, where we get all these p orbitals making the pi bonds just simultaneously overlapping together within a single orbital instead of 3 individual pi bonds. So you can create like networks of pi bonds where all the p orbitals just link up together and kind of take on all those electrons simultaneously, as opposed to it ever being the localized picture that we get within those localized bonding models. So localized bonding versus delocalized bonding, the idea is this. Delocalized bonding is what you get when you have resonance. So like there was a question, I think at the end of the notes in chapter 8 that said something like, which structure has a localized double bond? A localized double bond is one exactly where you think it is. Like formaldehyde on our previous slide. Formaldehyde has a localized double bond. It's exactly where you think. Nitrate has a delocalized double bond. It's a bond that resonates through the structure and is never really between just 2 distinct atoms. Benzene has 3 double bonds that are delocalized, that are not localized. So these bonds here are shown as if they were localized, but they're not ever really of that nature in the real molecule of benzene. So in the real molecule of benzene, the carbon-carbon bond distances are all equal. So if you take this distance to here in benzene, the real molecule, all those bonds are equal. Never, or 3 of the bonds shorter, 3 of them longer. This slide here I think will be a good starting point for us to review just kind of like resonance and some questions we could ask about it next time. And let's just wrap up today with our quiz. Our keyword for today is Dalton. So we are pretty much at the end of our coverage for midterm 4, so we can spend pretty much all day Friday reviewing, and then, like I said, a little bit of time before class on Monday as well. I'll send an announcement about practice exams, opening those up. There's a Friday review as usual. I'll get that notification out to you guys later this morning. So have a great day.